All right, in this section, let's review thermodynamics, starting with the first law of thermodynamics. So the first law of thermodynamics establishes that energy is conserved. So any energy that a system loses has to be gained by its surroundings and vice versa. Any energy lost by the surroundings is lost to the system or gained by the system. Any form of energy can be converted into another form of energy. From a practical standpoint, most energy transformations involve some loss of energy due to the transformation. For example, chemical energy is stored in gasoline. It can be converted to mechanical energy to run a car, but during that conversion from chemical to mechanical energy, some energy is lost due to friction and heat. This energy can be accounted for, so it's lost to the surroundings in the form of friction and heat. It doesn't get lost like destroyed. It's still there, but it's lost to the surroundings. We can account for it, but it cannot be recovered and used. All right, here are the major types of energy that you need to be familiar with. Mechanical energy is the sum of the kinetic and potential energies, where kinetic energy is the energy of motion of an object, and potential energy is energy stored due to an object's location. Chemical energy is the energy stored in the arrangement of the atoms of a substance. So maybe energy stored in bonds because of the way that the atoms are arranged. Thermal energy is energy due to heat and temperature. Thermal energy is associated with the motion of the microscopic molecules or the movement of those atoms of a substance. Radiant energy is energy associated with electromagnetic waves, like light. And the unit of energy that you need to be familiar with is the joule, which is abbreviated with a capital J. Continuing our discussion on the laws of thermodynamics, the second law of thermodynamics states that in an isolated system, the total entropy of the system always increases with time. Well, what is entropy? Entropy is a measure of randomness or disorder in a system. Any increase in randomness also increases the entropy of the system. Entropy can be decreased locally. One way to do that is like freezing liquid water. So going from a liquid to a solid will decrease the entropy of that water sample locally, but the entropy of the universe is always increasing. So the universe itself tends toward disorder and randomness, or another way of saying that is an increase in entropy. On the next slide, we'll list some changing conditions and describe whether entropy is increased or decreased. All right, let's predict entropy changes and say whether it would result in an increase in entropy or a decrease in entropy. So, beginning with the example that I talked about before with phases of matter. Going from a solid to a liquid to a gas, or from a solid straight to a gas would result in an increase in entropy because the atoms are becoming more disordered as you go from solid to liquid, liquid to gas, or directly from solid to gas. That means that the reverse, going from liquid to solid, gas to liquid, or gas to solid, just the reverse of each of these, would result in a decrease in entropy. The number of molecules. The more molecules present in a sample, the higher the entropy. The fewer molecules, the lower. The complexity of molecules. The more complex, the more random, or the higher the entropy. The less complex, the lower the entropy. Solubility. When a liquid or a solid dissolves in a solvent, so a liquid or a solid dissolves in a solvent, that increases the entropy. When a precipitate forms, so when a solid forms, or when a gas dissolves in a liquid, that decreases in entropy. So this is what I'm going to point out. We think of dissolving as increasing the randomness. Think of like salt dissolving in water. The salt crystals dissolve and separate into their ions, which is why we have an increase in disorder or an increase in entropy. But when a gas dissolves in a liquid, what happens? So think about when you dissolve carbon dioxide into your carbonated beverages. You're taking those gas molecules that want to be spread out anywhere they want to be, and you're forcing them into the volume of that liquid. So that decreases the entropy of that system. The third law of thermodynamics states that at absolute 0 Kelvin, the entropy of a crystalline substance is 0. And finally, the 0th law of thermodynamics establishes that two objects in thermal equilibrium have to be at the same temperature. Both of these laws lead us to our temperature scales. The 0th law tells us that a thermometer works. If the thermometer is in equilibrium with a substance, then it will read the temperature of that substance. The third law explains the Kelvin temperature scale because it's built on this idea that at absolute 0, the entropy of a crystalline substance is 0. There are 3 widely used temperature scales: the Fahrenheit scale, the Celsius scale, and the Kelvin scale. We know that water freezes at 32 degrees Fahrenheit or 0 degrees Celsius or 237 Kelvin, and that water boils at 212 degrees Fahrenheit, 100 degrees Celsius, or 373 Kelvin. There are conversions between Kelvin and Celsius and Fahrenheit given here. Kelvin relates the temperature to the kinetic energy of the substance's molecules. So 1 Kelvin is equivalent to 1 degree Celsius. You can see it's 100 degrees from 0 degrees to 100 degrees Celsius, 273 to 373 Kelvin, but it places this absolute 0 at 0 Kelvin.